So first what I wanted to do is just kind of introduce myself and my research group at Stanford. What we really are focusing on is looking at minimizing the environmental impacts associated with burning fossil fuels, which we seem to be doing at 24/7. And so if you look at the group here, you'll notice that there's a wide range of nationalities. And part of this is because the problem is not really a local problem. Emissions is a global problem. And it's really going to take global perspectives to figure out some of the solutions. So what I wanted to start my talk with is looking at what is the impact of CCS and thinking about a little thought experiment on expanding the impact of CCS. And so there was a paper that came out by Alan and others in Nature in 2009. And this was investigating preventing 2 degrees C warming. And what this paper showed is that it said that between the years 2000 and 2050, if the emissions, cumulative emissions, are say less than 1,000 gigatons over this 50-year period, there's going to be a 25% probability of warming beyond 2 degrees C. If the cumulative emissions are on the order of 1440, this probability increases to 50%. So then what I wanted to do is see, well, what are we doing today? And what does business as usual projections bring us to? And so assuming just from BP statistical review, we can assume increases of coal and oil and natural gas here. And then if we look at how much we emitted in 2011 on the order of about 31 gigatons, and projected based upon these increases, so this very simplistic projection in 2050, about 44. So the cumulative in this 50-year time period of CO2 emissions is on the order of 1790 gigatons in 2050. So again, a thought experiment. So we know that CCS is really one of several wedges of how we're going to prevent warming. And so if we look here, just trying to expand the impact of CCS, and we see business as usual, brings us to about a 6 degrees C rise with this 1790, assuming if we didn't do anything differently from here onward, which has been essentially our history of not really making an impact on changing the business as usual trajectory. And so if we think about trying to get down into these other regions, suppose that we took all of the coal that we burn and we replace it with natural gas. And so aside from Steve's talk earlier, if we don't include this concept or possibility of methane emissions, but simply using the statistic of we cut our emissions in half by replacing coal with natural gas, where does this bring us down to? It brings us down into the range of around 1,500 gigatons of cumulative CO2 emissions. Suppose that we were to do 90% capture from point source electricity sector. So this is coal and natural gas. We take all utilities associated with burning coal and natural gas for the electric sector. Brings us down to around 1288. So you can see even making these really significant differences still doesn't quite bring us in the range that we need to be in order to have these reduced probabilities for warming. So then if we go a little more extreme, and think about 90% capture, and not just from the electricity sector, but how could we do this from the transportation sector? So globally, the transportation sector represents about 25% of CO2 emissions. And this is a very difficult sector to tackle, because once you burn the gasoline in an automobile, the CO2 is distributed once it gets into the atmosphere. So it's one thing to think about point sources like utilities, but we've got 1 billion cars on the planet today and 1 billion in the pipeline. So these are committed emissions, and once the CO2 gets into the atmosphere, it's extremely dilute. And so to think about the transportation sector is difficult. You might think about onboard capture. Nobody has really developed a technology associated with that at this point. You can think of electrifying the transportation sector. So in a state like California, that might be a good idea, but if you live in Wyoming, where most of the electricity is from coal, that might not be the best approach. You can also think of biofuels as helping to replace some of these. And then you can also think about something like direct air capture, which I'm going to talk a little bit about today. So what I wanted to do also is think about where is CCS today? So how much impact have we made? And Granger alluded to this as well. There has not been a lot of progress, and certainly not the kind of progress we need to make significant impacts towards climate change reductions. So today we have 4 large-scale CCS projects that have been carried out monitoring sufficient to ensure injected CO2 is permanently sequestered. Combined, if you look at all of these projects, there's about 50 million tons of CO2 that's been stored. So you remember the order of magnitude before that I mentioned is on the order of 30 gigatons globally per year. So now we're talking millions of tons. There's 9 additional projects under construction. About 13 million tons of CO2 per year is expected to be operational by 2016. Now this is based upon an IEA CCS roadmap that came out in 2013 and a little bit of information from the Global CCS Institute in their final report as well. And since I've looked at those references before and up to today, some of those projects have since been canceled. So now the outlook is a little more bleak than it was previously. 2 demonstration projects for iron and steel plants. So this is an important concept. So there are products that we make that remove or that release CO2, and it's a chemical process. And these are products that we can't replace. So iron and steel, cement, and there's not, like the electricity sector, we can say, well, let's replace coal with natural gas, or let's replace coal and natural gas with renewables. But there are products that we rely on, especially in countries like India and China and in developing nations, that need cement, that need iron, and these kinds of building materials. And you cannot replace them. And there's a chemical process that produces them that emits CO2 into the atmosphere. And so it's really important, even though they represent a very small fraction of the global emissions, these are very important emissions to think about because they're not replaceable products. And they're not going to go away. And so, in addition to that, if we look at, one of the things is if you separate CO2, the big question is what do you do with it once you separate it? The scale and the magnitude is something we've never really seen before globally. It turns out that the CO2 pipeline transport is a mature technology. So if you are transporting it for utilization, like enhanced oil recovery, or if you're transporting it to store it in a geologic formation, in the United States, there's 3,700 miles of pipeline. Specifically for enhanced oil recovery projects, mostly in the Permian Basin in the Southwest. So CCS may be a primary large-scale option for emissions reductions from the industrial sector, as I mentioned before. And then also CO2 emissions from current systems. This is also something important. We have committed emissions. So, for instance, if you look at all of the power plants that are online today, the industrial facilities that are online today, we essentially are committed to an additional 550 gigatons of CO2 through 2035. This is an example of the large-scale CCS projects to date, and what I'd like to point out is that none of these projects, and these are also projected ones all the way up to 2019, none of these really, in this earlier stages, have to do with the utilities, so point source emissions. And that's because these are actually dilute systems. So today I am going to talk a little bit about direct air capture and how dilute direct air capture approach is, because CO2 now is about 400 parts per million in the atmosphere. If you look at power generation and you think about coal-fired power plants, you have a mixture of CO2, nitrogen, and water vapor primarily. And CO2 is about 15% at best from a coal-fired power plant. It's between 4 and 6% from a natural gas-fired power plant. Those are still dilute mixtures of gas. So the atmosphere is extremely dilute. But it turns out if you look at gas processing, so if you're recovering gas from the subsurface, oftentimes it has nitrogen, H2S, hydrogen sulfide, and CO2 in it. And that CO2 has to be separated. And it turns out that oftentimes that CO2 is much more concentrated than it would be from an emissions stack. So this is often why, for instance, gas processing, these projects have really kind of gotten started earlier than they would be from, say, a power plant. The other thing to note is that a lot of these projects don't actually have to do with permanent sequestration of CO2. So enhanced oil recovery is the motivation for a lot of these projects, and that's because enhanced oil recovery uses CO2. There's a cost on CO2. So you can say pay $20 a ton for CO2 if you use it for enhanced oil recovery. Enhanced oil recovery, in short, is essentially taking the CO2 in a supercritical form. You inject it into the subsurface. It's at those temperature and pressure conditions, and in that form that it's in, it's miscible in the oil, and it changes the properties of the oil, the viscosity, the density, so that the oil is more recoverable. So you can essentially recover oil that was very difficult to do earlier or before CO2 injection. But when the recovery of the oil takes place, the CO2 is mixed with the oil on the subsurface. And because CO2 costs something, the companies that are doing this have no interest in sequestering it. In this case, there are projects in which the sequestration is taking place, but the sequestration is small and it's controlled, and it's doing it so that monitoring efforts can take place to try and understand better the CO2 migration and its plume migration in the subsurface. But these approaches are able to take place, and these projects are able to take place mostly for the incentive associated with enhanced oil recovery, not necessarily to permanently store the CO2. We're just not quite there yet. So what I'd like to say here is that what if we continue to fail to make progress? And I'll follow up from Oliver's talk and Aldous Huxley, A Brave New World. And that's kind of what I see this next chapter potentially being, is a brave new world. Because where we're at today and the progress that we're making today is simply just not going to cut it if we want to think about impacting climate. And so the backup plans are these kinds of strategies. And so how I met Paul and how I'm here today was that we were on the committee looking at these kinds of approaches to make an impact. For instance, carbon dioxide removal, which I'll talk about, and then albedo modification, which isn't the highlight of today's symposium. So if we look at these different approaches, separate CDR approaches, separating into two categories. So the first category, I look at combined CCS. So what this means is, and oftentimes people will combine that phrase, carbon capture and storage, but in fact, these are two very separate topics. So carbon capture is a separation process. And then what you do with the CO2, whether it's utilization or whether it's storage, that's a whole nother issue. But there are technologies and approaches where these two things are embedded. And these are examples. So land management. Irreversible land changes from deforestation, decreased biodiversity. So in this case, land management approaches could include something like low tillage of soil. And so what that means is you're helping to fix or maintain the carbon in the soil. It might be planting trees in a region that was otherwise deforested. There are adverse and potential negative impacts associated with these approaches. Irreversible land changes, as I mentioned, and decreased biodiversity. For instance, if you are doing deforestation and then having to replant, it might be that what you're planting with is not as diverse as the stock that was originally in place. But in this case, there is no separate steps of separation and sequestration. They're embedded together. Similar to that is accelerated weathering in two different types. One is the ocean, so if we can change the chemistry of the ocean such that the ocean is able to draw in more CO2 than it currently does, that's one approach. Another is mineral carbonation on land. So there are a lot of natural rocks available that readily form carbonates with CO2. These are ultramafic rocks. I'm going to talk about this just a little bit as an example. And then there's also kind of what I call free alkalinity sources to making carbonates. And that's industrial byproducts. For instance, fly ash, cement kiln dust are examples where you have alkalinity meaning calcium or magnesium cations that can react with carbon dioxide to form carbonate products. And so in that case, you're actually doing the separation or the capture of CO2 from the atmosphere, and then you're reacting it with the rock to form the carbonate, and it's permanently sequestered via that chemical reaction. These other approaches are ones that decouple the separation from the storage. And these include the following. So bioenergy. Bioenergy is often coupled with the carbon storage, and it's termed BECCS, bioenergy with carbon capture and storage. It doesn't necessarily have to be captured or coupled with the storage. There's no reason that the bioenergy plant needs to be next door to where the CO2 is ultimately to be stored, but oftentimes these things are coupled. But you can imagine if you have bioenergy mixed, co-firing switchgrass with coal, for instance, and you do a separation on that process and capture the CO2, that CO2 could still be used for EOR. It doesn't necessarily have to be stored. But this is what you often hear about as BECCS. DAX is where you would take direct air capture. So you're actually capturing the CO2 from an extremely, extremely dilute mixture, the atmosphere, and then again, sorting out what to do with it next. And so I have separate here storage. And so I would say some of the limitations associated with that are understanding the quality of the reservoir and the injection rates and also the capacities. I'm going to bring us back to a little bit of these numbers later as well. So I'm just going to keep going here. So to give you a little bit of details on the Academy of Sciences or the NRC study that we were a part of, and I'm going to specifically just talk about the carbon dioxide removal report in which I was a co-author on. Our charge was really to look at the assessment of two classes of climate intervention, the ones that I've already mentioned. And we wanted to try and understand what's currently known today associated with the science and also the viability for implementation and give ideas of what are some research areas that could allow us to potentially move forward at some level in these areas. And then this is the group, and several of us are here today, Paul and Granger and Steve, and then if we can go on. So here, the recommendations from the committee is that first and foremost, there's no substitution for mitigation and adaptation. So if we go back to that business as usual approach, if we could think about the wedges associated with changing that trajectory, increasing energy efficiency, limiting deforestation, including carbon capture and storage, but in terms of a mitigation approach. These things should be really considered first and foremost, but the idea is if we continue to fail to do these at the rate that we need to impact climate, then these are the next things in line that we should think about. And the point is that these approaches that we have at our disposal today, for instance, a coal-fired power plant that's a more concentrated source of CO2 rather than direct air capture that's extremely dilute, they don't present as poorly defined and poorly quantified risks, and they're also at a greater state of technology readiness. The second recommendation was that research and development investments to improve methods of CDR and disposal at scales that matter. In particular, minimizing energy and environment and materials consumption, identifying and quantifying risks, lowering the costs, and developing reliable sequestration and monitoring. So what I'd like to do is just briefly give a couple of examples. One is mineral carbonation, and I choose these couple of examples because they are directly related to research. So I'm just being a little selfish because they're directly related to research that we've done in my group at Stanford. So I've alluded to this already, but with mineral carbonation, essentially what you're doing is you're taking some alkalinity source, and it could be an ultramafic rock, or it could be, as I mentioned, an industrial byproduct, but you need some source of alkalinity. Oftentimes to produce this alkalinity takes energy. And if you're having to, say, mine a rock, and you're having to grind it to increase the surface area so that it's reactive, or you're having to transport it from site A to site B, all of that takes energy and it costs money. If you have an industrial process that has fly ash, for instance, a coal-fired power plant, and it's not all fly ash that works. You need fly ash that's high in calcium, high in magnesium. But in these cases, coal-fired power utilities are happy to get rid of their fly ash. In fact, they might pay you to take it in some cases. And so it might be easier for them than to dispose of it on site, for instance. And so in this case, it makes sense to at least examine what the scale of those industrial sources are, which is what we did in this work. And this is just the chemical reaction. You react very simple, react with CO2, and you form this carbonate. These are some examples, the ultramafic rocks, olivine, serpentine. There's more, but those are some of the ones that you might have heard of before. And then again, some of these industrial byproducts. So what we did on this work is we did a life cycle assessment analysis. You can see more of this in Energy Environmental Science, this publication. And we looked at the extraction, we looked at the reactant transportation, the pre-processing. Again, as I mentioned, for instance, in some cases you would have to grind to get to the particle size, the surface area that you need for your material to be reactive. The chemical reaction itself, the post-processing, the transportation of the product, and the disposal or reuse, depending on what you're doing with the carbonate once you make it. All of these streams are proportional. So we have energy in red, the energy going in, the energy coming out, the solid going in, the solid coming out, the water in, the water out, CO2 in and out. And this is just, again, one example that I went through for the case of olivine. And we did this for a number of materials, and you can see those details. If you take one of those ultramafic rocks and you go through this entire process, you might ask, well, how much does that cost? And I didn't talk about the cost in our report, and we actually don't talk about cost here. But I did do an estimate, and that it turns out if you look at the energy that's required for each of these steps, and you assume that you're getting the electricity from natural gas, it comes out to about $1,000 a ton. So it's very expensive to mine these rocks and to get them to their reactive phase and to transport them and to create this aggregate of carbonate in the end. So that's the most expensive case, I should add, though, because you're having to actually mine it and make it reactive. But it gives you an idea of the scale. This is just a picture to give you an idea of the distribution of each of these things for each of these types of materials. Olivine at multiple temperatures, serpentine, cement kiln dust, fly ash, stainless steel slag. And you can see here, the CO2 emissions associated. The cement kiln dust is the lowest emissions ultimately, again, because it's free in terms of alkalinity, not completely, but pretty close to it. And there's not so much going into the pre-processing. We also wanted to say, well, if we were to make this aggregate, what could we do with it? We can't have stockpiles of aggregate in our backyards. And so that goes into having to find a market. A suitable market for something like aggregate could be the construction market. So road building, concrete. So in concrete, you have the cement, but you also have the rocks that the cement holds together to make the concrete. So what we did is we looked at the sand and gravel industry and looked at, imagine, displacing that. And then we also looked at, the aggregate market and imagine, instead of mining rocks for the aggregate market, suppose we could instead have synthetic aggregate and replace all of our aggregate with CO2-based aggregate. And so what this map is just showing is the availability of those industrial sources compared to the CO2 sources, so it overlaps well. So in terms of that, transportation costs would be potentially low. And you can find more details in this paper, but essentially the market is very small, and it would really looks at essentially on the millions of tons of CO2 rather than gigatons. And so finally, looking at that potential here, we see the black bar is the US emissions, annual emissions. And then here are the different scenarios. And if we look at the totals here, A versus B, so A is essentially, if we were to say, well, let's look at the lime production market in the United States and completely replace that with this. And then sand and gravel is B. And the reason we did that is because imagine, the case of these ultramafic rocks. There's enough ultramafic rocks out there to take care of our entire global CO2 problem. And so we needed to provide some kind of limit. There's the cost, it's $1,000 a ton potentially, but also how could we quadruple or even more than that? For instance, how could we ever take care of this? We would have to really multiply by multiple factors the entire sand and gravel industry. And what would that look like? So it doesn't seem terribly feasible, but it gives you an idea of the scale and the potential impact this mineral carbonation could have. The second part that I just want to mention briefly is direct air capture. And so there's several projects ongoing where they're trying to develop demonstration scale projects for this. This is a picture from David Keith's work. In addition to that, I wanted to talk about something called the minimum work. And so what this will do is give you an idea of the relative work associated with something like direct air capture, extremely dilute to other CO2 sources. So you've all probably heard of the organization ARPA-E, right? Most of you. Who has not heard of that, or you have? Okay. So ARPA-E put out one of its first solicitations back, I think it was in 2008, where they were looking at people to write proposals on carbon capture. And They got a lot of requests or proposals in from industry, from government, from academia, and before even sending them out to external review, they had to reject about 30%. And the reason why is they disobeyed the second law of thermodynamics. And so what this plot shows, what the minimum work calculation is, it's very simple. You take the first and second laws of thermodynamics, and you can calculate the minimum work required to do a given separation process. The only information you need is you need the starting concentration of CO2, you need to know how much CO2 you want to separate, and you need to know the purity that you want the CO2 to be on. That's it. And you need to know the temperature. So if you have that information, you can calculate what is the minimum work associated with separating, say, CO2 from a mixture of CO2 and nitrogen. And for instance, if you look at some of these numbers, so coal combustion, the minimum work is always going to be between 5 and 7 kilojoules per mole of CO2. And if you develop a new technology and you say, I can do it for 4, that's when your proposal gets rejected. So the idea is this is as low as you can go. And there's something called the second law of efficiency. So a real process is never going to be as good as the minimum work. A real process is where you have all of these unit operations like gas blowing, solvent pumping, regeneration. All of these unit operations have an efficiency associated with them, and those efficiencies aren't always terribly high. And so it turns out the real work is really kind of the deviation from this minimum work. And so even if somebody promises you something and they're close to it and they say, oh, it's an 80% second law efficiency, you still have to kind of worry about that technology. But I put this up here to give you an idea of the difference between direct air capture and some of these other approaches. And so direct air capture, oftentimes people will argue in that space, in that community. They'll say, hey, we don't need to do 90%. We don't even need 95% purity. We only want to capture 50%. And maybe we'll look at 80% purity. And so what I did is I just did this very back of the envelope, pretty easy calculation, a comparison of percent capture and purity. And it turns out no matter what, direct air capture is always going to cost between 19 and 21 kilojoules per mole of CO2. And you also have to be careful because as you decrease the purity, you're increasing the nitrogen content. And if you're going to put it in a pipeline for transport, and you have to put it in the liquid phase, and now you have to, you save here a little bit, but then you lose in terms of compression when you have to compress that very gas state mixture in a pipeline. So these other approaches, so if you look at natural gas, again, also dilutes is next in line, 6 to 9 kilojoules, coal combustion, and then coal gasification down here. So these are some tables that we came up with in the report to give you an idea of the magnitude that each of these approaches might have. So we looked at rate of capture and sequestration in terms of what's the best that they could do on an annual basis. And then what is if you look at cumulative up to 2100, what could these look like? And then what's the relative costs? And keeping in mind, in terms of ppm of CO2 in the environment or in the atmosphere, you have about, it takes about 18 gigatons of CO2 to decrease the CO2 concentration by 1 ppm in the atmosphere. And so these are just some examples. I just blew it up a little bit. So land management, pretty small impact, but it could also be very inexpensive to do it. Accelerated weathering, again, it could be expensive. It just depends on which approach you're using, whether it's industry or natural. Ocean iron fertilization, but the drawback there is you have significant risks associated with that approach. Bioenergy with capture. So one of the limitations associated with this is what is the available land area and making sure not to compete with food, especially as we talked about if we're thinking about population increasing to 9.5 billion, and then direct air capture. And these are, of course, potentially higher impact, but also more expensive. With storage, and this is my second to last slide, so thinking about the storage aspect, a lot of people say, these numbers seem very low because we have enough storage capacity to take care of all of our CO2. But the point is that, that's my timer. I think my time is up. So the point is with this is that Right now, if we are only sequestering on the order of millions of tons per year, and we need to increase that by 10 or 100, a factor of 10 or 100 to get to gigatons, how fast can we scale up things like injectivity of CO2? And what does that scalability look like? Not to mention the number of sites and geologic formations that we would have to inject into and the heterogeneity of all of those sites. And so what I did here is the limit is looking at the 2 degrees C scenario rather than the entire capacity of the geologic storage opportunities. And then finally, just to mention a few of the research directions that we're looking into, especially given that a lot of the population in the group here is students, and that we hope that you're motivated and excited to go into these fields and making a difference. So improving strategies associated with monitoring and of geologic sequestration, looking at the plumes and the migrations and the potential of inducing seismic effects and what does that look like. Continued research on combining biomass energy with CO2 capture and sequestration, and exploration of approaches that don't form and sequester concentrated CO2. Solicit and foster and develop approaches for scrubbing carbon dioxide from the atmosphere that hold the potential to bring the costs down to a potentially feasible range. Land management techniques that promote sequestration. And then finally, accelerated weathering as approaches that would allow conversion to stable or storable or usable carbonates and bicarbonates. And although we always say none of these is a silver bullet, but each one, in itself has an impact, and together and collective, they could represent a portfolio of solutions. And then this is just looking at the acknowledgements associated with those involved with the committee, and then questions if you have them.
I live in Western Pennsylvania, and there's, of course, a lot of folks around who aren't too happy about fracking. And in New York State, they've actually banned it. The notion of putting fluid underground is increasingly controversial, especially with earthquakes in Oklahoma and the like. So I recently asked Julio Friedman, who runs the DOE program on CO2 geologic sequestration, whether they were looking at any alternatives to deep geologic sequestration. And he said, no, there's plenty of resource there. There's no capacity constraint at all. Was that a stupid question on my part, to be worried that while there may be technological potential, there may be social interventions that limit how much of this we can actually do?
No, I don't think that was silly. I think that there's going to have to be a lot of effort towards communication to public about the risks associated, but not just the risks, but actually the scale of the risks, like giving concrete examples of what it might mean. And there's a lot that we've already learned, and maybe our next speaker will talk about this. But in terms of, for instance, with fracking with water, and looking at those kinds of, the history associated with that and what we've already done, or storage of natural gas in the subsurface and what we've learned from all of those experiences. I know that there was like a site or an opportunity in Germany where they were looking at storage of CO2 under one of the major cities there, and they had been storing natural gas under the city for years, and people were very comfortable with that. But the idea of storing CO2, it was a new idea, and I don't think it was well communicated, so it didn't move forward. But I think, as communication increases, as education increases, as public awareness increases, and people become more comfortable with the idea, and as more demonstration scale projects are online, so that we can actually prove and show that it can be done in a safe manner. But we need more of those kind of intermediate projects. I mean, there's 4 or 5 today, and we need 10, 100 times that. So I think, as we slowly increase that scale, those demonstration scale projects, and show and communicate and teach all of those things simultaneously, maybe we can get there. But
It seems like the energy that's, the amount of material that you actually have to process would be the largest materials processing project.
Absolutely, yeah.
Roughly 20 times the amount of concrete that's actually made. Have you thought about the manpower that would have to be committed to that and how that would draw from the private sector in terms of jobs? And then also the cost?
I haven't thought about the manpower, but what I do think about is in countries where, you think about, for instance, in India, 300 million people are without electricity in India, pretty much the population of the United States. The amount of development that's going to happen in India and in China in the future years, they're going to need things like concrete and iron and steel. And and so absolutely it's going to provide jobs, for people in those nations. But I don't know, the scale of what that would look like or where those resources would necessarily come from, to provide that manpower. But I know it's very competitive in China. There's many people for the one job that's available. And so if there's incentive to build more and expand, then there are definitely the people there to fill those positions. So, but.
Okay, thank you very much.